SwayamPrabha. Digital India. Educated India.
Analytical methods for wastewater parameters in the textile industry. Lecture number 17. Analytical methods for wastewater parameters in the textile industry is now going to be very crucial and important. Analytical methods for wastewater parameters in the textile industry are crucial for monitoring effluent quality, ensuring compliance with regulatory standards and optimizing treatment processes. Unless and until we are sure what are the levels, how do we design the treatment process? Here are some common analytical methods used for key wastewater parameters in the textile industry, that is chemical oxygen demand COD and biochemical oxygen demand, that is BOD. COD analysis is typically conducted using colorimetric methods such as dichromate method or potassium permanganate method. These methods involve oxidizing organic matter in the sample and measuring the amount of oxidizing agent consumed, which correlates with the COD concentration. BOD measurement involves incubating a sample in the dark for a specified period to allow aerobic bacteria to oxidize organic matter. The decrease in dissolved oxygen concentration during incubation is then measured, providing an estimate of the BOD concentration. pH measurement is commonly performed using pH meters or pH indicators. pH meter provide precise measurement of the acidity or alkalinity of the solution based on the concentration of hydrogen ions. Colorimetric method are often employed to measure color in textile effluent. These methods involve comparing the color of the effluent to standard color solutions by using spectrophotometry to quantify the absorbance of light at specific wavelength. Heavy metals analysis typically involves sample digestion followed by atomic absorption spectrometry, that is AAS, inductively coupled plasma mass spectrometry, that is ICP-MS, or inductively coupled plasma optical emission spectrometry, ICP-OES. These techniques can detect and quantify trace levels of heavy metals in the wastewater samples. Surfactant analysis may involve methods such as calorimetry, turbidimetry or fluorescence spectroscopy, depending on the specific surfactant compounds of interest. Surfactants can also be measured indirectly by assessing parameters such as foam height and stability. So, both by method of using a machine like turbidometry or calorimetry or fluorescence spectrometry, surfactants can be analyzed, or even by making a physical test like looking at the foam height and stability. Salt content. Salinity in wastewater can be determined by conductivity meters or titration methods. Conductivity meters measure the electrical conductivity of the sample. which is proportional to the salt concentration. Titration methods involve adding a known volume of silver nitrate solution to the sample to precipitate chloride ions, followed by back titration with a standardized solution to determine the chloride concentration. So, there are methods very well defined for the analysis. For COD, there is a oxidation solution of dichromate and permanganate. For BOD, there is a 5-day test at 20 degrees. It is allowed to incubate and see how oxygen consumption is taking place. And similarly, the pH can be determined by pH meter, and surfactants can be determined by turbidometer or calorimetry, or even by use of fluorescence spectroscopy. Color can be determined by spectrophotometer, that is color scan machine, and it at a proper wavelength it can be determined the quantity of the dye. Similarly, salt can be determined by titration method or by conductivity meter. Other parameters, additional parameters such as turbidity, total suspended solids, that is TSS, total dissolved solids TDS, and specific ions like chloride, sulphate may be analyzed by using methods such as turbidometry, gravimetry, ion chromatography or spectrophotometry. These analytical methods provide quantitative and qualitative data on various wastewater parameters, allowing textile industry professionals to assess effluent quality, identify sources of pollution, optimize treatment processes, and ensure regulatory compliance. Regular monitoring and analysis of wastewater parameters are essential for maintaining environmental sustainability and protecting human health. Benefits of analyzing crucial parameters of textile effluent. After all, why are we trying to analyze them? The question is that, is it important, and what are the benefits that we get from analyzing these parameters which we have just learned: COD, BOD, pH, color, heavy metals, surfactants and salt content. So, analyzing crucial parameters of textile effluent offer numerous benefits to both textile industry and environment. Compliance and regulation. Regular analysis ensures that textile effluent meet regulatory standards and environmental regulations set by governing bodies. Compliance with these regulations help avoid fines, penalties and legal consequences while promoting environmental responsibility. Pollution prevention. By identifying and quantifying key parameters such as COD, BOD, heavy metals and surfactants, textile manufacturers can pinpoint source of pollution and implement targeted measures to reduce or eliminate them. This proactive approach helps prevent environmental contamination and minimizes the impact of textile production on ecosystems and public health. So, what it means that if we know the levels of pollution, then only we can strategize how to remove that particular contaminant. So, analyzing these parameters and getting information about their levels has its own benefit. Optimizing or optimization of treatment processes. Analyzing effluent parameters allow textile facilities to optimize their wastewater treatment processes for maximum efficiency and effectiveness. By understanding the composition of effluent, operators can adjust treatment methods, chemical dosages and operating conditions to achieve optimal pollutant removal and overall treatment performance. Resource conservation. Efficient wastewater treatment and pollution prevention measures can lead to significant resource conservation, including water, energy and raw materials. By analyzing effluent parameters and implementing best practices, textile manufacturers can minimize water consumption, reduce energy usage in treatment processes and conserve valuable resources. So, resources, how they can be conserved, and by analyzing these parameters we will be in a win-win situation where these can be directly linked up by implementing best practices, and we can minimize the water consumption, reduce the energy usage and so on. Product quality assurance. Monitoring effluent parameters can indirectly contribute to product quality assurance by ensuring that wastewater discharge from textile processes does not contain harmful contaminants that could impact product integrity or consumer safety. This helps to maintain brand reputation and customer trust in the quality and sustainability of textile products. So, product quality assurance is also indirectly related to these analytical methods for analyzing these pollutants, because if the pollutant levels are high, process optimization can take care of that and they can be reduced. So, overall it is kind of a holistic treatment and holistic effect that it has if analysis is done effectively. Risk mitigation. Analyzing effluent parameters help identify potential risk associated with wastewater discharge, such as toxicity of aquatic organisms, soil contamination and corrosion of infrastructure. By understanding these risks, textile manufacturers can implement risk mitigation strategies to protect the environment, public health and their own operations. So, risk mitigation is also there. If some levels are going high, then it can be corrective measures can be taken and the effluent can be controlled not to have that high of that pollutant level. Sustainable practices. One of the benefits is that analyzing effluent parameters aligns with broader sustainability goals by promoting responsible environmental stewardship and resource management within the textile industry. By prioritizing pollution prevention, resource conservation and regulatory compliance, textile manufacturers can contribute to a more sustainable and environmentally friendly industry. So, overall, analyzing crucial parameters of textile effluent is essential for ensuring environment compliances, preventing pollution, optimizing treatment processes, conserving resources, assuring product quality, mitigating risk and promoting sustainability within the textile industry. So, overall we have so many benefits if we indulge in proper analysis of these parameters, that we can prevent the pollution, we can ensure that environmental compliances are practiced, and optimizing the treatment processes is facilitated, conserving the resources, assuring product quality. After all, what is that the consumer wants? The product quality matters a lot. Mitigating risk and promoting sustainability within the textile industry. COD and BOD analytical method. Now, let us try to look at these methods from the chemist's point of view. How does an analyst analyze these parameters in the laboratory? Analytical methods for measuring chemical oxygen demand COD and biochemical oxygen demand BOD are essential for assessing the organic pollution load in wastewater, including textile effluent. Here are the commonly used method for both the parameters. COD, open reflux method. The method involves refluxing a sample of wastewater with a strong oxidizing agent such as potassium dichromate, that is K2Cr2O7, sulfuric acid H2SO4 and silver sulfate Ag2SO4 in the presence of silver catalyst. The organic matter in the sample is oxidized to carbon dioxide and water, and the amount of oxidizing agent consumed is proportional to the COD concentration. The remaining unreacted oxidizing agent is titrated with standardized solution of ferrous ammonium sulfate to determine the COD value. So, it is a very simple open reflux method. There is another method which is called closed reflux method, similar to the open reflux method, but the sample is refluxed in a sealed reactor to prevent the loss of volatile organic compounds. This method is suitable for samples containing volatile organic compounds VOCs, or when accurate measurements of low COD concentrations are required. Quick COD test kit. There are rapid and convenient test kits that use calorimetric or tritimetric methods to estimate COD concentrations within minutes on the site. They typically involve adding reagent to the sample and measuring color changes or titrating to an endpoint to determine the COD levels. Biochemical oxygen demand, how is it analyzed in the laboratory? Standard BOD5 method. This method involves incubating a sample of wastewater in a sealed bottle for 5 days at a constant temperature, usually 20 degrees centigrade. During incubation, aerobic bacteria present in the sample consume organic matter and oxygen, leading to a decrease in dissolved oxygen concentration. After 5 days, the remaining dissolved oxygen is measured using a dissolved oxygen probe or titrating with a standardized solution of sodium thiosulfate. The difference between the initial and the final dissolved oxygen concentration represents the BOD5 value. Modified BOD method. Variation of standard BOD5 method exists, including the BOD7 and the BOD20 method, which involve incubating samples for 7 or 20 days as the number suggests. These modified methods are used when slower rates of biological activity are expected, such as in samples of high concentration of refractory organic compounds. So, there are very simple but very effective methods which can analyze COD and BOD. Respirometer method. These methods measure the oxygen uptake rate of microorganism in a sample using respirometer or oxygen sensor. by monitoring changes in dissolved oxygen concentration over time. Respirometric methods provide rapid estimates of BOD levels and can be used as alternative for traditional BOD5 measurements. So, there are other types of methods apart from BOD5, BOD7, BOD20. Respirometric method also exists. These analytical methods for COD and BOD are essential for assessing the organic pollution load in the textile effluents and optimizing wastewater treatment processes to meet regulatory standards and environmental requirements. The determination of pH in textile effluent is a fundamental parameter in assessing water quality and ensuring regulatory compliance. Here is an overview of the analytical method commonly used for pH determination. It is one of the easiest methods of determination. Every laboratory would have a pH meter. So, the first method is with the help of pH meter. Principle: pH meter measures the concentration of hydrogen ions, that is H plus, in a solution, which determines its acidity or alkalinity. The pH meter consists of a glass electrode and a reference electrode immersed in the sample solution. The glass electrode generates a voltage proportional to the hydrogen ion activity, which is converted to pH units by the meter. It has a very simple procedure, but yet one has to learn how to actually calibrate the pH meter. From time to time, if the pH meter is not calibrated, it may not give the accurate result. So, the procedure we will go through it. Calibration: before analysis, the pH meter must be calibrated using standard buffered solutions of known pH values, that is 4.01, 7 and 10.01 pH values of solution. Calibration ensures the accuracy and reliability of the pH measurements. Sample preparation: collect a representative sample of textile effluent in a clean container. Stir or swirl the sample to ensure homogeneity. Measurement: immerse the electrodes of the pH meter into the sample solution, ensuring that both the glass electrodes and the reference electrodes are fully submerged. Allow the pH reading to stabilize, typically within a few seconds to a minute, depending on the stability of the sample. So, it should come to us, one reading, it should not fluctuate. Recording: record the pH value displayed on the pH meter. Repeat the measurements if necessary to ensure consistency and accuracy, and ideally it should be repeated 3 times, and the mean value should be calculated. Cleaning and maintenance: rinse the electrodes with distilled water after each measurement to remove any residue or contamination. Restore the pH meter properly and perform regular maintenance according to the manufacturer's instruction to ensure optimal performance. And let me tell you, because the textile effluent is not a clear solution, this post cleaning of the pH meter becomes mandatory and essential. Interpretation: pH value below 7 indicate acidic congestion, while pH values above 7 indicate alkaline or basic conditions. A pH of 7 is considered neutral. The pH of textile and effluent can vary depending on the factors such as type of dyes, chemicals, salts and processes used in the textile manufacturing. The pH of the textile effluent was in the range of 5.79 to 12.88. It is obvious from the result that most of the samples were highly alkaline, above the permissible limits of the Environmental Protecting Agency, that is EPA. Although the range of the textile effluent was found to be 5.79 to 12.88 from different levels of processing, but that is not what is recommended by EPA for the discharge values. Consideration: ensure that the pH meter is properly calibrated before each use to maintain accuracy and reliability. Handle the electrode with care to prevent damage or contamination, which can affect measurement accuracy. Use appropriate safety precautions when handling textile effluent, including wearing protective equipment and working in a well ventilated area. So, all the good laboratory practices GLP should be kept in mind. Using a pH meter for the determination of pH in textile effluent provides a rapid and accurate result, enabling textile manufacturers to monitor water quality, adjust treatment processes and ensure compliance with regulatory standards. Color determination of the textile effluent. The color of the textile effluent is an important parameter to assess, as it can indicate the presence of dyes and other contaminants. Several methods can be used to determine the color of the textile effluent, with spectrophotometry being the most commonly used technique. Here is an overview of the analytical method for determining the color of the textile effluent using spectrophotometry. What is the principle behind the spectrophotometry analysis? Spectrophotometry measures the absorbance or transmission of light by a sample across a range of wavelengths. The color of the solution is determined by the wavelengths of light absorbed or transmitted by the sample. In the case of textile effluent, the presence of dyes and other colored compounds will result in the absorption of specific wavelengths of light, which can be quantified using a spectrophotometer. Procedure. What is the procedure for color determination? Sample preparation. Collect a representative sample of textile effluent in a clean, transparent cuvette or sample cell. If necessary, filter the sample to remove any particulate matter that may interfere with the measurement. Baseline measurement. Fill a separate cuvette or sample cell with distilled water or a blank solution and insert it into the spectrophotometer. Set the spectrophotometer to 0 absorbance or 100 transmission at the desired wavelength range to establish a baseline measurement. Measurement. Transfer the prepared sample to of the textile effluent into a clean cuvette or sample cell and insert it into the spectrophotometer. Select the appropriate wavelength or wavelength range for color measurement, typically within the visible light spectrum, that is from 400 to 700 nanometer. Procedure. Record the absorbance or transmission values displayed on the spectrophotometer for the sample at selected wavelength or wavelengths. Repeat the measurement if necessary to ensure consistency and accuracy. Data analysis. Calculate the color of the textile effluent based on the absorbance or transmission values obtained from the spectrophotometer. This may involve comparing the sample's absorbance spectrum to known standards or using specific equation or algorithm to quantify color intensity or hue. So, here either we compare with a known standard and see whether the wavelength is matching or not, so that we can identify the color and subsequently identify the dye. Otherwise, we can just take a spectrophotometric analysis and get the spectrum to see what is the lambda max of the unknown dye. Interpretation. The color of the textile effluent can be expressed in various ways, including absorbance values at specific wavelength, calorimetric values like alpha color, or qualitative descriptors like hue, intensity, etc. The presence of certain dyes or contaminants in the effluent may contribute to specific color characteristics, which can be identified and quantified using spectrophotometric analysis. So, the beauty of this instrumentation method is that one can actually identify the dye from its lambda max value, and that is a very accurate way of identification of the dye that has been used. Consideration. Ensure that spectrophotometer is properly calibrated before each use to maintain accuracy and reliability. Let me tell you here that for analysis, every equipment should be periodically calibrated in order to ensure that it is functioning accurately. Handle the sample and cuvette with care to prevent contamination or damage that could affect measurement accuracy. Use appropriate safety precautions when handling textile effluent, including wearing protective equipment and working in well ventilated area. Even in the previous method, I had told that good laboratory practices have always to be kept in mind while working in an analytical lab. Spectrophotometric provides a versatile and reliable method for determining the color of textile effluent, allowing textile manufacturers to monitor effluent quality, assess the effectiveness of treatment processes, and ensure compliance with regulatory standards. Now, let us see how the heavy metals are determined in the textile effluent. Analytical methods for determining heavy metals in textile effluent are essential for assessing environmental pollution and ensuring regulatory compliance. Here is an overview of the commonly used method for determining heavy metals in textile effluent. The first method is with the help of atomic absorption spectrometry, that is AAS. The other method is conductively coupled plasma mass spectrometry, which is ICP-MS. The principle of AAS and ICP-MS are widely used for analytical techniques for quantification of heavy metals in liquid samples such as textile effluent. Both methods rely on the principle of measuring the absorption characteristic wavelengths of light by metal atoms in the sample. So, it is a method in which the absorption of light, just like the way we saw the color was also dependent on the absorption of light. Here heavy metals and metals are affected by the light and they absorb light. So, these both are useful, AAS and ICP-MS. They excite the heavy metal and bring it to a principle where measuring the absorption characteristic of the wavelength that they have absorbed is what is the main function. Procedure: say sample preparation. Collect a representative sample of the textile effluent in a clean container depending on the specific requirements of the analytical method. Sample preparation may involve filtration, acid digestion or dilute to ensure that the heavy metals are present in a suitable form of analysis. Now, this is a very crucial stage because the metal has to solubilize first and should be at a dilution level where it can be identified and quantified correctly. If it is too concentrated a solution, the results may go haywire. Therefore, sample preparation becomes very crucial. Instrument calibration. Prepare calibration standards by diluting certified reference materials containing known concentrations of heavy metals with appropriate solvents. Calibrate the AAS or ICP-MS instrument using these standards to establish a calibration curve relating the measurement signal of the concentration of each heavy metal. And in the case of AAS, it is calibrated with 4 ppm of copper sulphate solution. So, if the 4% of known solution shows 4% as its absorbance through the absorbance, then that means that the machine is well calibrated and can be used for other metal ion identification and quantification. Instrument analysis. In the case of atomic absorption spectrometry, that is AAS, atomize the sample by heating it in a flame or graphite furnace and then measure the absorption of light at characteristic wavelengths for each metal using a hollow cathode lamp. So, one by one the lamp is changed and different metals from the same textile effluent solution can be analyzed one after the other. The absorption intensity is proportional to the concentration of the metal in the sample, and this is following Beer-Lambert's law completely. Those who understand Beer-Lambert's law will know that absorption of light is directly proportional to the concentration of the ion. Inductively coupled plasma mass spectrometry ICP-MS atomize the sample by introducing it into high temperature plasma generated by inductively coupled plasma source. The metal ion in the sample are ionized and then detected and quantified based on their mass to charge ratio using a mass spectrometer. Data analysis. Quantify the concentration of each heavy metal in the textile effluent sample based on the calibration curve obtained from the instrument calibration. Repeat the analysis for multiple samples to ensure accuracy and precision. Interpretation. Heavy metal concentrations in textile effluent are typically reported in units of mass per volume, milligram per liter or microgram per liter, or mass per mass, that is milligram per kilogram or microgram per kilogram. Compare the measured concentration of heavy metals in the effluent to regulatory limits or guidelines to assess compliance with the environmental regulation and standards. Consideration, because this is a very crucial analysis, as we know that heavy metals have very serious implications to human health as well as to aquatic life. Handle the sample and reagents with care to avoid contamination and ensure accurate results. Even sample preparation and handling of the sample requires special consideration. Follow established laboratory protocols and quality assurance procedures to maintain the accuracy and reliability of the analytical measurements. Dispose of hazardous waste materials generated during sample preparation and analysis in accordance with relevant regulations and safety guidelines. Atomic absorption spectrometry, that is AAS, and inductively coupled plasma mass spectrometry ICP-MS are highly sensitive and selective techniques for determining heavy metals in textile effluent, providing valuable information for environmental monitoring, pollution control and regulatory compliance. And let me tell you that between the two, between AAS and ICP-MS, ICP-MS can actually analyze in a much faster way more number of metal ions from the same sample at a shorter time, and so it is very cost effective. Although the plasma that is generated is generated from argon gas, which is a little expensive. So, in the case of AAS, we have to change every time the hollow cathode lamp, and then one by one only the metal can be analyzed. So, now let us look at how the surfactants are determined in textile effluent. Analytical methods for determining surfactants in textile effluent are essential for assessing water quality, understanding the environmental impact of the textile manufacturing and ensuring compliance with regulations. Here is an overview of the commonly used method for determining surfactants in textile effluent. So, the method could be calorimetry assay or chromatography. So, the principle is that for calorimetric assay are based on the reaction between the surfactant and specific reagents which produce a color change that can be quantified spectrophotometrically. The most common calorimetric assay for surfactant is methylene blue active substance, that is MBAS method, or the cationic surfactant active substances CAS method. These methods involve the reaction between the surfactant and the methylene blue or other dye reagent to form colored complexes, and the surfactant will be qualitatively making these complexes, and they will be spectrophotometrically determined. The intensity of the color developed is proportional to the concentration of surfactants in the sample, which can be measured using spectrophotometer. Chromatographic method. Chromatographic method such as high performance liquid chromatography or gas chromatography are more specific and provide detailed information about the individual surfactant compound present in the effluent. Now, HPLC could take place only if it is a high molecular weight non-volatile surfactant, but GC could be used when it is a volatile surfactant. Reverse phase HPLC with UV detection or mass spectrometry is commonly used for the separation and quantification of surfactants in complex matrices like textile effluent. So, even reverse phase HPLC with UV detector can be used for this purpose. Now, what is the procedure? Sample preparation. Collect a representative sample of textile effluent in a clean container. If necessary, filter the sample to remove particulate matter that may interfere with the analysis. For calorimetric assays, prepare standard solutions of surfactants with known concentrations to establish a calibration curve. Dilute the effluent sample appropriately to ensure that the surfactant concentration falls within the linear range of the calibration curve. For chromatographic methods, extract the surfactant from the effluent using appropriate extraction techniques such as liquid-liquid extraction or solid phase extraction prior to analysis. So, both the method require sample treatment and sample preparation in a very different manner. Calorimetric assay. Add the appropriate reagent to the effluent sample according to the chosen method, whether we want to use MBAS method or CAS method. Incubate the mixture for a specified time to allow the color reaction to occur. Measure the absorbance of the resulting colored complex using a spectrophotometer at the appropriate wavelength. Compare the absorbance reading to the calibration curve to determine the concentration of the surfactant in effluent sample. Now, here you will see that because the color has to develop, therefore, certain specific time period has to be left between the reagent, appropriate reagent, whether it is MBAS or CAS reagent with the textile effluent sample, so that the surfactant specifically reacts with that reagent and develops color. Measure the absorbance of the resulting colored complex using a spectrophotometer at the appropriate wavelength. So, you will notice that even here in the calorimetric method, we are using spectrophotometer, and in other substances also like the dye, and even for ICP-MS method and AAS method, all the absorption of light technique was the main principle. Compare the absorbance reading to the calibration curve to determine the concentration of the surfactants in the effluent sample. Chromatographic technique. Inject the prepared sample extract into the chromatographic system and separate the surfactant using the chosen chromatographic method, whether it is reverse HPLC or HPLC with UV or reverse phase HPLC and UV, etc. Quantify the surfactants based on their peak areas and peak heights relative to the standard solution of known concentration, because in HPLC method you have to have a calibration standard. Against that the sample is analyzed, because otherwise an independent peak has no significance and cannot be quantified. It can be qualitatively analyzed that there is only one peak and one surfactant, but in order to know which surfactant is present, we have to calibrate it or take first a standard run that will give a peak at a particular retention time, then match the sample surfactant and its retention time. If the retention times are matching, then from the peak height of the known the unknown is quantified. Identify individual surfactant compounds based on the retention times or mass spectra obtained from the chromatographic system. So, if the system, if it is an LC-MS, then it becomes easier because the mass spectro can give accurate results. Retention times can still be deceptive. Two compounds can have the same retention time, but may not be structurally the same, but mass fragmentation pattern of the mass spectra will accurately tell which is the compound. Interpretation. Interpreting the result of the calorimetric assay or chromatographic analysis in terms of surfactant concentration, that is milligram per liter or microgram per liter, or individual surfactant compound present in the effluent sample can be done. A calibration method is mostly adopted so as to match with the standard compound. So, just now I said that if we want to quantify, we need to have a standard of that surfactant. Then only with a known concentration of the standard surfactant, we can find out the concentration of the unknown surfactant. Consideration. Follow standard operating procedures and quantify assurance protocols to ensure accurate and reproducible results. Choose analytical methods that are suitable for the specific type of surfactant present in the effluent and meet the required sensitivity and selectivity. Handle hazardous reagents and waste materials according to safety guidelines and regulatory requirements. We have to be very particular that while even analyzing, no contaminant should get into our body, because good laboratory practices have to be kept in mind even when they are in small quantities and handling the samples. Handle hazardous reagents and waste material according to the safety guidelines and regulatory requirements. Both calorimetric assay and chromatographic methods provide valuable information about the surfactant content in the textile effluent, enabling textile manufacturers to monitor effluent quality, optimize wastewater treatment processes and ensure compliance with the environmental regulation. After all, why are we analyzing these parameters? Firstly, because these parameters are very crucial and are responsible for making the pollution load, and therefore, each of these parameters need to be accurately analyzed. So, in conclusion, we can say determining textile effluent parameters through analytical method is crucial for assessing water quality, environmental impact and regulatory compliance in the textile industry. So, having understood the importance of analysis, the analysis of these crucial parameters including pH, color, heavy metal, COD, BOD, TSS, TDS and surfactants. We need to find out how much is present. Only when we know how much is present, we can make a strategy for the optimization of the different processes, which all processes are contributing largely. And in one of the lectures I had shown that sizing and desizing contribute largely, as well as dyeing and printing also increases the COD, BOD largely. So, this we could know only when analysis was done accurately these values were available. We also saw in one of the lectures that how cotton mill contributes more than synthetic mill, and this would not have been possible if proper analytical methods would not have been followed. COD, BOD, pH, color, heavy metals and surfactants. These methods provide valuable information on the presence and concentration of the contaminants, which can affect water quality, treatment processes and environmental toxicity. Because if we do not know how much of heavy metal is present in the textile effluent, how do we control it? And how do we prevent from running into the water bodies? So, only when we know that the levels are very high, then we can prevent the running into the water bodies, and first they will be treated, and then only when the levels are low, again by analysis we will know from which level it has been reduced to which level, and once it comes to the permissible level set up by the regulatory bodies, only then we can run it into the fresh water bodies. Overall, we can say that the selection of appropriate analytical method depends on factors such as specific parameters of interest, sample characteristic, regulatory requirements and available resources. By accurately measuring textile effluent parameters, manufacturers can optimize processes, minimize environmental impact and ensure sustainable practices in textile industry, which means that analysis plays a big role. This analysis, if we are not carefully doing it and if we do not have the correct values, can be very misleading and can create a havoc and have an adverse effect on the environment. So, as conscious citizens, keeping in mind the sustainability and the environmental impact on human health and ecology, we need to understand the importance of analysis of these crucial pollutants, and some of them are very harmful as being carcinogenic or mutagenic or endocrine disruptor. Therefore, their content and stringent regulation by the government plays a very big role. We have to bring it down to that permissible level. So, we can say that analysis is equally important, because only knowing that these are present, like pH is adverse, surfactant is very high, heavy metal is very high, it does not help. What helps a textile manufacturer is that how much is there and how can we reduce, because then only the mill workers will optimize the processes. So, with this we have come to an end of this lecture. Thank you.